Even though Saturn has always been associated with its rings, in recent years, this planet holds more than just the title of Lord of the Rings. It is now also the undisputed King of Moons. It has more known moons than all the other planets of the solar system combined. These moons come in various shapes and follow a wide range of orbits, often moving within the ring system itself. Some of them carve out the famous gaps in the rings, while others actually help maintain their structure, preventing the rings from spreading outward. It's a complex, dynamic system whose fascinating features are still being studied to this day. So, in this episode, I invite you to dive deeper into the intricate ecosystem of Saturn's ring and major moons, a system that has essentially formed a miniature solar system around one truly remarkable planet. The first thing worth saying is that almost all the stunning images of these extraordinary moons exist thanks to the Cassini spacecraft. It spent 13 years in the Saturn system, giving it plenty of time to observe the local moon zoo, many of which genuinely surprised us. Cassini didn't just take pictures, it also tasted them, analyzing their constituent particles. So everything we'll talk about today, and every image you'll see, is thanks to that one mission. I never get tired of saying that, alongside the Voyagers, Cassini may well be one of the most revolutionary scientific space missions in history. As of now, the International Astronomical Union recognizes 274 moons of Saturn, making this gas giant a clear leader in this category, far ahead of any other planet. But don't be surprised if Google shows you a different number, especially if you're watching this episode a year or two after it was released. That's not my fault. Saturn just keeps getting new moons discovered on a regular basis. In fact, the last batch added 128 new moons, just 2 months before this video was published, in March 2025. That's the beauty of advancing astronomical technology. The moon count will keep going up. But the big question is, how much will it grow, and will we ever know the final number? It's no secret anymore that Saturn's rings themselves are made up of an uncountable number of icy particles. These range in size and mass, from tiny grains of sand to boulders the size of trucks, houses, or even mountains several kilometers across. So the question of how many moons Saturn has inevitably brings us to another question. What even counts as a moon? For Saturn, this is especially relevant, since its entire ring system could be viewed as trillions of tiny moons, all orbiting the planet along their own paths. In reality, astronomy doesn't have a strict definition for the word moon, because every attempt to pin one down has proven futile. So due to the difficulty of distinguishing between the largest ring particles and the smallest moons, determining the exact number of Saturn's moons might actually be impossible in principle. Still, the sheer number of known objects we call Saturn's moons isn't just a coincidence, and the rings aren't the only reason for that. Around every planet, there's a region in which its gravitational pull is strong enough to hold on to other bodies as satellites. Technically speaking, the Sun acts equally on a planet and on any of its moons, so don't assume that Earth pulls the Moon more strongly than the Sun does. It's more accurate to say that the Earth and Moon orbit the Sun together, as a pair. However, Earth's gravity is strong enough to locally retain the Moon in orbit, and together they revolve around a shared center of mass that happens to lie inside our planet. This region, where a planet can gravitationally dominate and hold on to satellites, is called the Hill sphere, named after American astronomer George Hill, who first introduced the concept. For Earth, given its distance from the Sun, the Hill sphere extends about 1.5 million kilometers from its center. The Moon, which never drifts more than 400,000 kilometers away from us, lies comfortably within that region, so there's no danger of the Sun stealing it away anytime soon. What's important here is that the size of a planet's Hill sphere depends not only on its mass, but also on its distance from the Sun. The farther a planet is from our star, the larger its gravitational domain becomes. That's why, even though Jupiter is the most massive planet, its Hill sphere is actually smaller than Saturn's. The Lord of the Rings has a Hill sphere that's nearly twice as large. And that, in part, explains why Saturn currently holds the record for most moons. Now, based on that logic, if you were placing bets, which planet would you expect to have the highest number of moons in the long run? That's right. If Neptune weren't so distant and dim from Earth, it would probably surprise us with the number of objects orbiting it. Maybe one day we'll see dedicated orbital missions to the ice giants. And who knows? One of them might eventually dethrone Saturn as the king of moons. So Saturn has an incredibly diverse family of moons, varying in their orbits, sizes, chemical compositions, and of course, their shapes. Some are large, spherical worlds, often referred to as planet-like, but there are even more that come in irregular forms, resembling potatoes, sponges, seeds, or even dumplings. Some moons orbit Saturn on wide, elongated paths, often moving in the opposite direction of the planet's rotation. Others live right inside the rings themselves, playing a key role in shaping and maintaining the structure and dynamics of the rings. And in return, the rings also help define the environment of these moons. These so-called ring moons are typically only a few kilometers in diameter, and there might be hundreds of thousands of them, but only a handful have been directly detected. After the Voyager flybys, scientists began to suspect that the many gaps seen in Saturn's rings might be caused by tiny, unseen moons around 10 kilometers in diameter. For example, in the Encke Gap, which is 325 kilometers wide, astronomers noticed wavy edges, suggesting the gravitational influence of some hidden object. By the late 1980s, using models of those gravitational patterns, researchers were able to estimate the mass and orbit of this mystery moon. Finally, in 1990, a detailed reanalysis of Voyager images led to its discovery. Later on, Cassini captured it in close-up. So, meet Pan, one of the first confirmed ring moons. And yes, fans of Ukrainian cuisine will definitely appreciate its appearance. This dumpling Pan is one of Saturn's innermost moons, orbiting just 134,000 kilometers from the planet, right inside the Encke Gap. It's only 28.2 kilometers across, but its gravity is strong enough to noticeably disturb the tiny ice particles in the rings on both sides of it. Those striking wave patterns you see, they result from the difference in orbital speeds between Pan and the surrounding ring particles. Particles closer to Saturn orbit faster than Pan, so when they feel its gravity, they get slightly pulled back, slowed down, and start to clump together into what are known as density waves that stretch for hundreds of kilometers along the ring plane. On the outer edge, it's the opposite. Pan moves faster than the ice chunks out there, so it pulls them forward, giving them a boost in orbital velocity. These particles also form waves, which you can clearly see in the stunning images taken by Cassini. By the way, besides those beautiful ripple patterns, you might also notice a couple of faint ringlets right inside the Encke Gap. One of them aligns perfectly with Pan's orbit, suggesting a direct connection. But the shape and presence of the second ring hint that another, even smaller moon may be lurking nearby, one that hasn't been discovered yet. Daphnis resides within the 35-kilometer-wide Keeler Gap and plays a similar role to Pan. It too went unnoticed in the Voyager images at first, but its gravitational effects on the ring edges made scientists suspect its presence. In 2005, it was finally spotted in Cassini's photos. Daphnis is incredibly small, just 7.6 kilometers in diameter, but Cassini got close enough to reveal some of its surface features, including a subtle equatorial ridge. By the way, Pan has a twin brother, another dumpling-shaped moon named Atlas, which orbits along the outer edge of Saturn's A-ring. It turns out this quirky shape is a common trait among ring moons. Scientists believe that these distinctive equatorial ridges are made of dust and ice particles that Pan and Atlas may have gathered from the ring plane around them. Since both moons have extremely low densities, even lower than that of solid water ice, they're likely very porous inside and possess weak gravitational fields overall. This makes it easy for fine icy dust to accumulate in a ridge without spreading out evenly across the surface. At the same time, those ridges can't grow too large because Pan and Atlas both spin on their axes, and centrifugal forces effectively fling away any excess material. In fact, if you look at this Cassini image, you can see a faint ring of material lining up exactly with Atlas's orbit, just like with Pan. This suggests that many other diffuse ringlets found within Saturn's ring gaps might also be tied to as-yet undiscovered moons. For example, none have yet been found inside the Huygens and Maxwell gaps, but something has to be hiding there. Interestingly, Atlas was long thought to be responsible for maintaining the shape of the A-ring, which is why it was named after the mythological Atlas, the Titan who held up the sky in Greek mythology. However, scientists now agree that the A-ring isn't actually resting on Atlas's shoulders. Another moon is doing the heavy lifting here, and we'll be talking about that one a bit later in this episode. In 2004, As the Cassini spacecraft entered orbit around Saturn, it captured detailed images of the A ring. Remember, that's the outermost of Saturn's 3 main rings. One of the first surprises awaiting scientists was the discovery of 4 faint, oddly shaped streaks. These streaks appeared double-lobed and resembled airplane propellers, which is how they got their nickname, propellers. It didn't take long for scientists to realize they were looking at indirect evidence of tiny moonlets embedded in the ring plane. These little moons, roughly 100 meters across on average, are too small to be imaged directly, but the trails they leave behind give them away. Despite the name, these structures don't spin like an aircraft propeller. They always point in the same direction as the moonlet moves through the ring. Their strange shape might seem hard to grasp at first, especially when viewed in schematic form, but it's actually something we can understand. Again, remember, ring particles orbit at different angular speeds depending on how far they are from Saturn. The inner parts of the rings rotate faster than the outer parts. So around a tiny moonlet in the rings, some particles will be moving faster and some slower. Specifically, particles on the moonlet's left, closer to Saturn, move faster and overtake it, while those on the right, further out, lag behind. From the moonlet's own frame of reference, the particles on the left appear to move forward, and those on the right seem to fall back, even though all particles are technically orbiting in the same direction around Saturn. This differential motion explains why the moonlet's gravitational effect stretches in both directions, forming the distinctive 2-lobed shape of the propeller. Of course, these moonlets are far too small to carve out full gaps in the rings like Pan does. Instead, they simply disturb the surrounding material, creating this curious pattern. That said, there are some larger propellers, like this one here, which seems to have partially cleared a path around itself. Its central moonlet may be around 1 kilometer in diameter. What's especially fascinating is that Saturn's propellers may hold valuable scientific insight. Since the planet's ring system can be viewed as a miniature version of the early solar system's protoplanetary disk, these propellers are like tiny analogs of forming planets. It's possible that early Earth also collected material around itself within the dusty gas disk, generating a similar pattern in its early days, before growing more massive and eventually clearing a full gap like Pan. That's why scientists are eager to study this phenomenon more closely. Interestingly, not all small moons necessarily create visible propellers. Cassini once imaged a small object within the B ring, yet there was no trace of a propeller-like pattern around it. This observation happened during Saturn's equinox, when the sun's light was nearly edge-on to the ring plane. That lighting caused even the tiniest bumps to cast long shadows, making it possible to detect the object at all. At the time, its shadow stretched 41 kilometers, which means the moonlet rose about 200 meters above the ring plane. Assuming it orbits within the plane, that puts its estimated diameter at about 400 meters. Scientists believe the absence of a propeller in this case has to do with the ring's density. The B ring is denser than the A ring, where most propellers have been spotted. So here, it's harder for a moonlet to carve a gap, and the surrounding material quickly refills any disturbances. Oh, and by the way, some of the propellers have names. Many are named after notable pioneers in aviation history. Let's recall from a previous episode the peculiar narrow ring of Saturn labeled with the letter F. It's often considered the strangest of them all. Located about 3,400 kilometers beyond the outer edge of the A ring, the F ring is flanked on either side by 2 intriguing moons: Prometheus, measuring 102 kilometers across, and Pandora, about 84 kilometers wide. These 2 were first spotted during the Voyager 1 flyby, just a year after the F ring itself was discovered by Pioneer 11. They're commonly known as shepherd moons because of the way they influence the F ring, controlling its shape and behavior. Think of them as cosmic herders, corralling a stream of icy particles into a narrow, twisted band only about 100 kilometers wide. Thanks to Cassini, we've even got stunning video footage of this dynamic process, revealing intricate details in action. For example, look at what happens to the ring under the gravitational influence of Prometheus. The moon tugs at ring particles, drawing them out into thread-like features called mini-jets. It also creates wave-like patterns that resemble carved channels in the ring. All of these complex interactions make the F-ring one of the most dynamic and ever-changing structures in Saturn's system. With each orbit of the shepherd moons, the ring bends, twists, and reshapes itself into strange and beautiful forms. Interestingly, Saturn isn't the only planet with shepherd moons. Uranus, for instance, has them too. Cordelia and Ophelia guide its epsilon ring in much the same way. More broadly, the term shepherd moon can refer to any satellite that influences the shape or dynamics of a ring system. In that sense, Pan, Daphnis, Atlas, and many of Saturn's other moons could also be considered shepherds in their own right. Prometheus and Pandora, and the F-ring itself, have some rather unusual and intriguing neighbors. Janus and Epimetheus orbit between the F-ring and the path of Mimus, one of Saturn's major moons. Janus has an average diameter of about 180 kilometers, while Epimetheus is slightly smaller at 120 kilometers. These two are rarely discussed separately because their orbits are so close that, under normal circumstances, they should have collided long ago. To put it into perspective, their orbital paths differ by just 50 kilometers, less than the size of either moon. And yet, they've found a way to avoid a crash. Every 4 Earth years, Janus and Epimetheus simply swap orbits. When Cassini arrived at Saturn in 2004, Epimetheus was the inner moon of the pair, closer to the planet. Remember, the closer you are to Saturn, the faster your orbital speed. So Epimetheus was slowly but steadily catching up to Janus on the slightly wider track. When they finally draw near, they begin to tug on each other gravitationally in opposite directions. Janus pulls Epimetheus upward, giving it a boost in velocity. As a result, Epimetheus shifts to a higher orbit where, according to Kepler's laws, objects move more slowly. At the same time, Janus loses just enough momentum to drop into the lower orbit where things orbit faster. This can be a bit confusing. Gaining angular momentum doesn't mean spinning faster around the planet. It actually lifts you into a wider orbit which moves more slowly. So, the end result is a graceful orbital switch. Janus becomes the faster inner moon and begins chasing Epimetheus until the cycle repeats. The last exchange happened in 2010. This kind of celestial choreography is known as a co-orbital configuration. Despite their nearly overlapping orbits, the two moons never actually collide, or even come closer than about 15,000 kilometers from one another. Janus and Epimetheus remain the only known pair in the solar system where two bodies of comparable mass have entered this kind of gravitational partnership. But there's more. They also interact gravitationally with Saturn's rings. In doing so, they absorb angular momentum from the ring particles. Simply put, these moons, along with Pandora, help keep the rings from spreading outward. Ring particles frequently collide, and some gain enough momentum to try and drift to wider orbits. But because there are moons just beyond the A ring, those particles transfer momentum to them instead, and stay in place. In turn, the moons slowly inch away from Saturn as they absorb these tiny pushes. However, the fact that Atlas, Pandora, Janus, and Prometheus are still orbiting relatively close to the planet suggests that this ring-driven migration hasn't been happening for billions of years. It must have started only recently, on a cosmic timescale, perhaps just a few million years ago. And that, once again, supports the idea that Saturn's ring system is young. Much, much younger than Saturn itself. Many space enthusiasts recognize it, even if they don't know its name. Though Darth Vader lived a long time ago in a galaxy far, far away, the Death Star seems to have been inspired by something much closer to home. Mimus. Despite its striking resemblance to the Empire's ultimate weapon, Mimus is a small and quiet moon, technically the first among Saturn's so-called major moons. It's still not massive enough to form a perfect sphere, and so it looks more like an egg with an average diameter of about 400 kilometers. It orbits Saturn at a distance of 186,000 kilometers, about half the distance from Earth to the Moon, and completes a full orbit in just 22 hours and 36 minutes. Like many of Saturn's moons, Mimus is tidally locked, always showing the same face to the planet, but not the face with its famous eye. That massive crater is named Herschel, in honor of the moon's discoverer. It spans 130 kilometers, about a third of Mimus's entire diameter. a collision that powerful would have drastically reshaped the moon and very nearly shattered it. On the opposite side of Mimus, you can still see signs of where the impact waves traveled through and cracked the surface. What's curious is how heavily cratered Mimus is, indicating that its surface is quite old. And yet, if you compare it to a moon like Enceladus, which literally erupts with icy geysers, Mimus starts to look very strange. That's because Mimus orbits even closer to Saturn than Enceladus, and it has a more eccentric, elliptical orbit. This means it should, in theory, experience even stronger tidal heating than its famously active sibling. But Mimus is eerily quiet, and that doesn't make much sense, at least not if the heating mechanism that powers Enceladus is as straightforward as we think. This is what's known as the Mimus paradox, and it remains one of the great mysteries of the solar system. Any hypothesis that explains the presence of liquid water beneath Enceladus must also account for its apparent absence beneath Mimus. And yet, in 2014, scientists observed a peculiar libration in Mimus's orbit, wobbles that resemble those of Enceladus. This was considered indirect evidence of a subsurface ocean, but the idea was quickly challenged because Mimus doesn't show any external signs of internal activity. No surface fractures like we see on Europa, for example. Instead, it was proposed that the unusual motion could be due to an asymmetric distribution of mass inside Mimus, possibly caused by the same massive impact that formed Herschel. However, in 2024, new research suggested that the libration is too slow to be explained by a solid mass anomaly alone. It could only be accounted for by the presence of a liquid ocean beneath the crust. So why don't we see any surface signs of it, especially with the constant tidal stretching and squeezing of the moon? That remains an open question. Even though Mimus doesn't replenish Saturn's rings with material the way Enceladus does, it still plays a significant role in shaping the system. In fact, Mimus is believed to be responsible for the Cassini division. No, Mimus doesn't orbit inside Saturn's most famous ring gap, but it does help create it. Here's how. The particles near the edge of the B ring are in orbital resonance with Mimus. For every 2 orbits these icy particles complete, Mimus goes around Saturn once. This means the ring material consistently encounters the moon's gravitational influence at the same point in their orbit, getting nudged inward each time. Over time, this clears out the space we know as the Cassini division. So, it's not an unknown hidden moon carving the gap, it's orbital resonance with Mimus. Similarly, the outer edge of the A ring is in a 7-to-6 resonance with the co-orbital moons Janus and Epimetheus. That is, for every 7 orbits completed by ring particles, the moon pair makes 6. In fact, many resonances can be found throughout Saturn's rings, but not all the gaps and not all the thousands of fine ringlets can be explained just by known resonances and known moons. So the truth is, we still don't fully understand how Saturn's rings work. Few worlds in the solar system are as captivating as Enceladus. It is truly a superstar, not just among Saturn's moons, but among all known moons in the system. Back in the wild youth of your humble narrator, when I was still a university student, the Cassini mission had already been revealing Saturn to us for several years. At the time, Enceladus easily topped the charts in popular science literature. The discovery of water geysers erupting from its south pole remains one of the most important astronomical findings in recent history. I'm not exaggerating when I say that it was this very moon that first sparked my deep interest in space, and in the solar system in particular. Roughly 300 kilograms of water ice particles are released every second from the now famous Tiger stripes, forming Saturn's E-ring. Cassini flew directly through these plumes, collecting and analyzing particles not only from the jets themselves, but also from the E-ring material. Among the most important discoveries was the detection of silica particles, tiny grains of silicon dioxide. This compound can only form where liquid water interacts with rock at temperatures above 90 degrees Celsius. This, along with other pieces of evidence, strongly suggests the presence of hydrothermal vents on Enceladus, places that, here on Earth, teem with life even in complete darkness. In fact, some theories propose that life on Earth itself may have originated in such environments. It's no wonder this tiny moon has become one of the most promising targets for future space exploration. In 2024, the European Space Agency named Enceladus as its top scientific priority for upcoming missions, with planning already underway for a launch sometime in the early 2040s. NASA also has its own mission concept to Enceladus, recommended in the most recent decadal survey in planetary science. However, considering NASA's current funding constraints, we shouldn't hold our breath waiting for that mission to get off the ground. So, for now, scientists must continue combing through Cassini's treasure trove of archival data. One of the more recent studies suggests that the famous plumes might not originate directly from Enceladus's subsurface ocean. A research group proposed that friction along the tiger stripe fractures could melt local surface ice into a slushy mixture, which then becomes the source of the jets. If this turns out to be true, the plumes may not actually reflect the composition of the deep ocean beneath. Perhaps, but the orbital libration of Enceladus still indicates that a global ocean exists. And when you have liquid water, a source of energy, and basic organic molecules, that's already more than enough reason to keep looking. Even if no microorganisms are ever found on Enceladus, the fact that all the basic ingredients for life exist so far from the Sun would still be one of the most profound discoveries in planetary science. Tethus, Dion, and Rhea are the next stars of our show, and these three moons share a lot in common. Tethys is slightly less cratered than her sisters, but she still bears the hallmark look of a Death Star, with a massive impact crater nearly 400 kilometers wide called Odysseus. Tethys is the fifth largest moon of Saturn, with a diameter of over 1,000 kilometers, specifically 1,066 kilometers. Yet despite her size, she has the lowest density, just 0.98 grams per cubic centimeter, of all the major moons in the solar system. This suggests that Tethys is made almost entirely of water ice, with only a small fraction of rocky material mixed in. The crater-rich surface implies great age, but it's surprisingly bright for such an old object. Since Tethys orbits within the diffuse E-ring, it's likely that icy particles from the ring constantly bombard her surface, effectively refreshing it. And just as a reminder, that very ice originates from the geysers of Enceladus. Aside from the prominent Odysseus crater, Tethys's most iconic feature is the Ithaca Chasma, a vast canyon system several kilometers deep, stretching across 3/4 of the moon's circumference. Because this giant rift cuts through heavily cratered terrain, scientists believe it formed early in Tethys's history. One leading theory suggests that water inside the moon froze and expanded, cracking the outer shell apart in the process. Interestingly, Tethys even has a couple of her own companions, Telesto and Calypso. Though technically moons of Saturn, these two co-orbit with Tethys, maintaining fixed positions relative to her as they travel around the planet. They reside in the stable Lagrange points. Telesto leads Tethys by 60 degrees, and Calypso trails 60 degrees behind. This configuration is strikingly similar to the Trojan asteroids of Jupiter, which share the planet's orbit around the Sun while gathering at its L4 and L5 Lagrange points. Dion also has her own Trojan-like companions, Helene and Polydeuces, who share her orbit around Saturn. Dion herself is only slightly larger than Tethys, with a mean diameter of 1,123 kilometers, but she has about 1.5 times the density. This suggests she's made of roughly equal parts ice and rock. Just like Tethys and Mimus, Dion is tidally locked to Saturn, and this creates some noticeable differences between her two hemispheres. First, her leading hemisphere, the one facing forward in her orbit, has fewer impact craters than the trailing, rear-facing one. That's actually counterintuitive. The leading side should be taking more hits from space debris, much like the windshield of a moving car collects more bugs than the rear window. Scientists suspect that perhaps a few billion years ago, Dion may have been facing the other way, but a long history of impacts, which formed the current craters, might have eventually flipped her orientation. Second, the trailing hemisphere is significantly darker than the leading one. The contrast isn't as dramatic as on Iapetus, but it's still clearly visible. In this case, the leading side appears cleaner and brighter, likely due to continual sandblasting by micrometeoroids and icy particles, refreshing its surface. And third, Dion's trailing hemisphere displays a striking system of bright linear features. At first glance, these look like massive fractures, but in reality, they're a dense network of fine cracks that don't significantly alter the surrounding terrain. After Cassini's high-resolution images, scientists concluded these bright streaks resemble canyon walls where darker material has broken away, revealing the pristine, reflective ice underneath. There's even a hypothesis that these streaks could be ancient analogues to the tiger stripes of Enceladus, features that once might have been geologically active, but have since gone quiet. In that sense, the bright cracks might be fossil evidence of Dion's past tectonic activity. Though Dion no longer shows signs of internal activity, she plays a key role in Enceladus's current behavior. Through orbital resonance with Enceladus, Dion helps maintain the eccentricity of its orbit. That orbital stretching, in turn, fuels Enceladus's tidal heating, and with it, its famous icy geysers. So, in a very real sense, Dion deserves some credit for the drama unfolding on her smaller neighbor. Finally, we come to Rhea, a truly large moon. She's the second largest satellite in the Saturnian system and the ninth largest in the entire solar system. As we've already mentioned, Rhea shares many similarities with her sisters, Dion and Tethus. She's also bright, reflecting a great deal of sunlight, and is tidally locked to her planet. Her density is slightly lower than Dion's, but higher than that of icy Tethus, suggesting she's composed of about 3/4 water ice and 1/4 silicate rock. However, during a close flyby, Cassini measured Rhea's moment of inertia and found that the moon is likely not differentiated, meaning she doesn't have a layered internal structure. Instead, her rocky and icy components are likely mixed throughout, much like the interior of Jupiter's moon Callisto. This might be because Rhea orbits farther from Saturn than Dion or Tethys, receiving less internal heat from tidal forces. As a result, her interior may never have melted, and so never separated into distinct layers. The lack of geological activity is also evident from her heavily cratered surface, which is even more scarred than those of Dion or Tethys. But what really surprised scientists was the possibility that Rhea might have its own ring system. In 2008, Cassini detected evidence of material orbiting Rhea, marking the first time rings had ever been suggested around a moon. Later, another research team analyzed additional Cassini images and didn't find any rings, so this question remains open. Another fascinating discovery came in 2010 when Cassini detected a very thin atmosphere around Rhea, specifically an oxygen-based one. This was also a first for any moon. It's thought that charged particles moving through Saturn's magnetic field bombard Rhea's surface, splitting water ice molecules into their components. Of course, calling it an atmosphere is a bit generous. The molecular density here is about 5 trillion times lower than Earth's at sea level. It's more accurate to call it an exosphere, a faint envelope of gas with a density of around 1 million molecules per cubic centimeter. Interestingly, a similar exosphere has also been detected around Dion. Now take a look at this photo of Dion, taken by the Cassini spacecraft. At first glance, many of you might not notice it, but that dim, blurry planet in the background? It's not Saturn, as you might assume at first. It's Titan. We often underestimate the sheer scale of this giant. Titan has a diameter of 5,150 kilometers. It's not just Saturn's largest moon. It actually holds 96% of the total mass of everything orbiting the planet. That means only 4% of the mass is shared between all the other moons and rings combined. So, yes, Titan's grandeur is undeniable. It's the second largest moon in the solar system, but if we factor in its atmosphere, it easily claims the #1 spot, even beating Ganymede. Titan is a world unto itself, larger than Mercury and about 1.5 times the size of our moon. And it's got a dense, beautiful atmosphere, about 1.5 times heavier than Earth's. Chemically, Titan's atmosphere may be quite similar to what once enveloped Earth during the early stages of life's emergence. Before Cassini, no one really knew what lay beneath that thick yellowish haze, but radar mapping from the spacecraft revealed something extraordinary. The surface is far too cold for liquid water, but it turns out it's just right for liquid hydrocarbons, methane and ethane. Scientists discovered that on Titan, these substances don't just form lakes and rivers, they even fall from the sky as slow, heavy raindrops. At the time of recording this episode, NASA's Dragonfly mission has already been approved. The next step is finalizing the spacecraft's design and moving into construction. The planned launch date is July 2028, with arrival on Titan expected in 2034. Of course, there's always a looming threat to missions like this, and it currently lives in the White House. Let's hope NASA's budget doesn't get slashed and Dragonfly remains untouched. If all goes well, we're in for a wealth of new discoveries about this incredible world. Honestly, it's hard not to love Titan. It's truly one of the crown jewels of our stellar neighborhood. You'd think we could wrap up this episode with magnificent Titan, but no, not quite yet. In fact, the moons that lie beyond Titan's orbit are a whole different story. If there were ever a competition for the oddballs of the solar system, some of Saturn's outer moons would easily top the list. Just take a look at Hyperion. At first glance, it might resemble a small asteroid, with a bizarre surface texture that looks like a kitchen sponge or perhaps a wasp's nest. But don't let its looks fool you. Hyperion is actually quite large, 410 by 260 by 220 kilometers, just slightly smaller than Mimus, for instance. It's the largest known irregularly shaped moon in the solar system. But that's just the beginning. Its average density is about half that of water ice, indicating a truly porous structure, not just on the surface but throughout. Scientists believe Hyperion is made up of loosely bound icy chunks held together by gravity, with plenty of empty space inside. In fact, estimates suggest it's about 40% porous. Based on its composition and appearance, it may well be a remnant of a larger body that was shattered long ago. And there's more. Thanks to an orbital resonance with Titan, Hyperion follows a highly eccentric path, and unlike most large moons of Saturn, it is not tidally locked. It does have a rotational period of about 13 days. But here's the fascinating part. Its irregular shape and offbeat orbit make its spin completely unstable. Hyperion tumbles through space in what mathematicians classify as chaotic rotation. In other words, its rotational state at any given time is fundamentally unpredictable. It's the only known moon in the solar system with a confirmed chaotic spin. Farther out still lies the orbit of Iapetus, more than 3.5 million kilometers from Saturn. This striking moon is best known for its dual-tone appearance. Its leading hemisphere absorbs nearly all sunlight, reflecting just a few percent, while its trailing side reflects around 60%. This yin-yang moon shows the greatest brightness contrast of any known object in the solar system. For a long time, scientists puzzled over the cause of this bizarre two-tone surface. Eventually, the discovery of a faint ring associated with the moon, Phoebe, offered a clue. It turns out that Iapetus's leading hemisphere is constantly being coated in dark material from Phoebe's ring, which explains the extreme coloration. Phoebe, the moon responsible for painting Iapetus, is another truly unique satellite, well known to fans of science fiction, particularly those familiar with the Expanse series of novels. This roughly spherical, 210-kilometer object orbits Saturn at a much greater distance than Iapetus. It's about 13 million kilometers from the planet, taking approximately 1.5 Earth years to complete a single orbit. What makes Phoebe even more intriguing is that its orbital plane is steeply tilted relative to Saturn's rings, and it orbits in the opposite direction of the planet's rotation. This retrograde motion, along with Phoebe's relatively high density compared to Saturn's other moons, suggests it didn't form around Saturn. Instead, it's likely a captured object from the more distant reaches of the solar system. Phoebe was actually the first moon Cassini encountered upon arriving at Saturn. Mission planners specifically designed the spacecraft's trajectory to make a close flyby. This moon is extremely dark, reflecting only about 6% of incoming sunlight, which further connects it to the outer solar system, where similarly dark material is common. One hypothesis about Phoebe's origin links it to the Centaurs, objects from the Kuiper belt that have migrated inward toward the Sun. These bodies are found in the region between the Kuiper belt and the asteroid belt, and are considered a transitional class between these two distinct populations. Centaurs are of great interest to scientists because they are believed to be relatively unchanged building blocks of the early solar system. So far, no centaur has been directly explored, making Phoebe a potential first. Lastly, Phoebe is considered the source of Saturn's largest and yet most elusive dust ring. Constant impacts from micrometeoroids eject fine particles from its surface, spreading them across vast distances. This ring isn't visible to the naked eye and was only discovered by detecting its thermal glow in the infrared spectrum. For over a century, Phoebe remained Saturn's most distant known moon. It wasn't until the early 2000s that astronomers began discovering smaller boulders gravitationally bound to the planet. Many of these objects have inclined, retrograde orbits like Phoebe's, and are therefore grouped with it into what's called the Norse Group, which now includes 197 objects. As a result, the majority of Saturn's known moons actually have retrograde orbits. In this diagram, they're marked in red. They're called the Norse Group simply because their names are derived from Norse mythology. There are also the Inuit Group, 36 moons, and the Gallic Group, 17 objects, whose names come from Inuit and Celtic mythologies, respectively. All these objects are relatively small, just a few kilometers across at most, and are likely fragments of larger planetesimals captured by Saturn in the early stages of its formation. After numerous collisions, among themselves, with other moons, or with comets, they were shattered into smaller pieces, now orbiting on distant, chaotic paths. The debate over whether all these bodies should be classified as moons is ongoing. Most agree that not every piece of rock or ice deserves the title, yet where to draw the line remains unclear. But to me, that question isn't the most important one. Every new object discovered adds immense value, not only to our understanding of the Saturnian system, but of the solar system as a whole. Even the tiniest fragments, seemingly insignificant debris, are actually witnesses to dramatic events from the distant past. Yes, the number of known moons will likely continue to grow, but ultimately, it's not the total count that matters most. What matters is that behind each of these objects lies a story, one we are only just beginning to uncover. Thank you, friends. I hope you enjoyed this two-part journey to Saturn. If you did, please consider showing your appreciation with a like or a comment. Fortunately, there are still many fascinating corners of the solar system we haven't yet explored, so stay tuned. See you in the next episode, and take care of yourselves.